I am Devanku Bidkar. I am associated with the Condition Monitoring Laboratory in the Department of Electrical Engineering, Visvesvaraya National Institute of Technology, Nagpur. I am currently working on an industry-oriented project titled Detection of Abnormal Lithium-Ion Cell in an EV Battery Pack. This project is funded by Arise Industries, Vadodara, Gujarat, and is being carried out under the guidance of Professor Makaran Sudhakar Ballar, Professor in the Department of Electrical Engineering at VNIT Nagpur. Let me first start by sharing the motivation behind this work. Today we are witnessing the growing adoption of electric vehicles where the EV battery pack acts as the heart of the EV. In a typical lithium-ion battery pack, the cells are connected in an array structure consisting of cells connected in series and parallel arrangements to meet the required power demand of the appliance connected. Now on the screen, you can see the scaled down model of a typical EV battery pack configuration. This battery pack is a 6 series 4 parallel configuration in which 6 cells are connected in series and 4 cells are connected in parallel, making a total of 24 cells. Each cell is rated at 4 volt and 2.6 ampere hours of capacity. Thus, in this battery pack, a total voltage of 24 volt and a capacity of 10.4 Ah can be obtained. The approximate power that can be delivered by this battery pack is around 250 watt. Now in the diagram we can see these terminals B1, B2, B2, B3, B3, B4 and so on up to B6, B7. They are respectively called as the strip voltages. So in all in this battery pack we are going to obtain 6 strip voltages and the total terminal voltage of the battery will be obtained across the terminals B1 and B7. The problem statement is to determine the weak cell or cells in this 24 cell array structure. Now, how do we define a weak cell? A weak cell is a cell which has a very less voltage, approximately around 3 volt. This weak cell tends to act as a burden on other healthy cells. Like if this weak cell is substituted at any location in the battery pack, then this weak cell will start to extract the electric charge from other healthy cells. So what is happening? The other healthy cells are losing their voltage, their essential voltage. And that's why the overall rating of the battery pack, the overall terminal voltage of the battery pack is suffering. That is, it is decreasing. On the same side, what is happening? This weak cell itself is extracting the electric charge from the other cells. That's why it is getting heated. So there is a chance or a probability that this weak cell might enter the stage of thermal runaway. So if this problem is not addressed early, then the overall rating and the capacity of the battery pack will be impacted. The identification of this weak cell is a very great challenge. That's why rigorous literature survey was conducted and the problem statement was fixed, based on which an analytical foundation was laid and a polynomial equation was mathematically derived, as you can see on the screen. So this equation will help us to detect the location of the weak cell in our battery pack. The coefficients A1, A2 till AN are based on the battery pack configuration details, the healthy cell voltage, the abnormal cell voltage, and the internodal resistance value. We first tested this analytical approach through simulations in MATLAB environment. So as you can see on the screen, we have simulated a 6 series 4 parallel battery pack in MATLAB and some of the results are shown on the screen. To implement this practically, we developed a prototype in CMEC laboratory. It is named as WAVES. WAVES is the weak cell analysis and verification for the EV systems. As you can see here on the hardware setup, this is our WAVES setup. In this WAVES setup, you can see there is a breadboard circuit. This breadboard circuit is our voltage divider circuit. We pretty much know that Arduino microcontroller cannot handle voltages beyond 5 volt. So we have to maintain security at its analog pins. So when we are extracting the strip voltage data from our battery pack, that is intentionally reduced below 5 volt and that is fed to our microcontroller. This microcontroller does contain our proposed algorithm which is input in this. So this is our WAVES setup. The operations of the WAVES is very simple. First step is to ensure that our battery pack is in a neither charging nor discharging condition. This is our first step. Second step is to ensure that the battery pack is not connected to the battery management system. So in the hardware setup, we can see that the battery pack is not connected to any BMS. Third thing, we have to make sure that our battery pack is connected to our WAVES system. So this WAVES system will obtain all the strip voltage data and feed it to the microcontroller. You can see here that for this first battery pack, all cells in this battery pack are normal, that is at healthy condition. So when this battery pack is connected to our wave system, we are going to observe on the display what are the results. As we can see on the screen, nearly all the strips are close to 4 volt. So after running the program, we can see that there is no weak cell detected. Now we are going to thermally validate our findings. So now I'm going to project this thermal camera on our battery pack and we are going to see the temperature. We see one thing, that the less than 35 degree Celsius. Now we are going to check for our second battery pack. So as you can see, this is our second battery pack. Now this battery pack is connected to our wave system. This battery pack is again covered, so we don't know the inside condition of this battery pack. So with the help of wave system, now we are going to see what is observed on our display unit. All the strip voltages are nearly 4 volt, and clearly on the screen it can be seen that all cells are operating normally. Now is the time to replace an healthy cell of this battery pack intentionally with a abnormal cell. So in my hand I have one abnormal cell whose voltage is very less, and now I am going to replace it in strip number 5 and at location number 4. Now here we can see that intentionally an abnormal cell has been substituted in strip number 5 and at location number 4. Now is the time to move towards our third battery pack. This battery pack has been borrowed from a battery manufacturer for our testing purpose, and now for this battery pack we are going to see the results of the wave system. The display shows that the abnormal strip detected is strip number 3. We can also see that strip 3 has the least voltage of 3.6951 as compared to the other strips, and the location that has been identified is cell number 4. I'm proud to share that the WAVES project has achieved its intended goal. The key highlights of this project are accurate detection of the weak cell through strip voltage measurements. The conditions are neither charging nor discharging condition, independent of the battery management system data. Third thing, that we have successfully done our validation through thermal imaging, and in this way the WAVES project has been completed. I sincerely thank the Department of Electrical Engineering, Visvesvaraya National Institute of Technology Nagpur, the Director of VNIT Nagpur, and Arise Industries Gujarat for their support in successfully completing this project. Thank you all for watching this video. Please share your feedback and comment if you liked it. I'm going to demonstrate the hardware setup where we are going to validate our WAVES approach on this capacitance based methodology. In the capacitance based methodology, it is pretty much understood that as the age of the lithium ion battery pack increases, the value of the capacitance also increases, and this is the important health parameter for the battery pack. So now on this setup you can see that there is one healthy battery pack. In this healthy battery pack, all cells are in a healthy condition. Nearly all cells are at 4 volt. So on the charging unit you can see the value of all the strip voltages are around 4 volt. Now I have connected this battery pack with this function generator. What this function generator does, that it injects a 10 millivolt 1 kilohertz voltage in our battery pack, and after that we get the output of the voltage and current on this DSO. So you can see on the screen of the DSO there is one voltage waveform, DC voltage waveform, and current waveform. So now I am going to switch on this function generator. Switching on this function generator, that means the 10 millivolt sinusoidal AC voltage will now be injected into the battery pack. These are the points through which the 10 millivolt AC has been injected to this battery pack. And now on the DSO, we are going to save the voltage and the current values. So now this file has been saved for the healthy case condition. Similar process we are going to adopt for a weak cell condition. So what is going to happen now? Deliberately, that we are going to replace a healthy cell, let's say in strip number 1, with this abnormal cell. So the healthy cell of strip 1 at location number 4 has been replaced with a weak cell. And now on the charging unit you can see that the voltage of the strip 1 has dropped to 3.79, nearly 3.8 volt. Now we are going to again switch on this function generator to inject the 10 millivolt sinusoidal AC in this weak battery pack. Again we are going to save the voltage and current data for this battery pack. Now after this I am going to feed this CSV data that was obtained from this DSO to our discrete Fourier transform algorithm, that is DFT algorithm. From that DFT algorithm we will evaluate the capacitance, and from that capacitance we are going to observe that during the healthy case condition and the abnormal case condition, what is the nature of the values of the capacitance. Now on the screen you can see the tabular representation for our validation process. In this first column, we can see the number of weak test cases that were conducted. The first case is the healthy case condition where all the cells were at healthy state, that is nearly all the cell voltages were near to 4 volt. And the rest 13 cases were the weak cases in which intentionally a healthy cell of that particular strip was replaced by a weak cell. So this second column depicts that information. Here we can see S1C4. This indicates that a healthy cell in strip number 1 and at location number 4 was replaced by a weak cell. Similarly, S1C2 means a healthy cell in strip 1 and at location 2 was replaced by a weak cell. This process was reiterated till 6 strips. So in every strip, we replaced a healthy cell by a weak cell twice, making up a total of 13 cases. For every case, we can observe the values of the strip voltages that were recorded. So for this, let's say for this second case where a cell in the first series and at location number 4 was replaced by a weak cell, we see that the voltage of that strip reduced or dropped down as compared to the other strips. So here the drop down value is 3.85. Correspondingly, we also tried to validate the weak cell location by recording the temperature using the thermal imaging camera. The temperature that was recorded was 36.6, which is more than the temperature that was recorded in a healthy state condition. Also, we validated the same using the capacitance based method. So for this weak cell condition, the capacitance process was performed wherein 10 millivolt AC voltage was injected in the battery pack, and the output voltage and current was obtained, based on which the discrete Fourier transform was applied and the capacitance was evaluated. So we see in this column that as compared to the healthy state condition, the change, the percentage increase in the capacitance was found to be 5.05. Similarly, for the other test cases, we observed that the values of the strip voltage, the corresponding strip voltage, tend to decrease. The temperatures of that particular weak cell is also more as compared to the healthy cell condition, and the capacitance value seems to be more. So this validates our waves approach in two ways. First, the thermal validation, proposing that the weak cell itself extracts a charge from the other healthy cells, that's why its temperature is more. And the second validation is by our capacitance based approach, where after inducing the weak cell in the battery pack, the capacitance of the battery pack is found to be more than that of the healthy state condition. Thank you.